In this last video on 1.2, I want to show you how we can use Gauss elimination to solve more efficiently some problems we've seen before, more specifically one in section 3.1, number 19. And the problem reads as follows. You have to find scalars, C1, C2, and C3, for which the equation C1 times a first vector plus C2 times a second vector plus C3 times a third vector equals to the vector minus 1, 119, and we want to find those the scalars such that the equation is satisfied. Notice we can write this equation the following way, like C1 times a vector, C2 times another vector, C3 times another vector. So essentially what we have here is a linear combination of V1, V2, and V3. Okay. And we want to figure out if that's equal to some vector b. B being this vector here. Okay, so let's try to do this. Now, I will convert this vector equation into a system of equation by equating the first coordinate, the second coordinates, and the third coordinates. If I do this, it means that C1, so looking at the first coordinates, C1 times 1 plus 3C2 plus 0C3 must be equal to minus 1. So that's looking at the first coordinates, right? And doing the same with the second coordinates, we get minus C1 plus 2C2 plus C3 is equal to 1. And finally, we get 0C1 plus C2 plus 4C3 equal to 19. And that's, so we need to solve this system. Okay? So I can use Gauss elimination. So every time we have a solid system, Gauss elimination is the way to go. So the augmented matrix is, well, it's what? It's 1, minus 1, 0, 3, 2, 1, 0, 1, 4, and minus 1, 1, 19. So notice, so this is for your notes, notice it is the matrix with V1 in the first column, V2 in the second column, V3 in the third column, and B in the fourth column. So this is interesting because it shows us that we can go backwards and say that every linear system can be looked from the point of view of finding a linear combination of the columns of the coefficient matrix being equal to the constant vector. So let me say that again. If we look at the coefficient matrix, okay, that's 1, 3, 0, minus 1, 2, 1, 0, 1, 4, okay, and its columns are V1, V2, V3. So whenever we have a linear system, we can actually say, oh, we're actually trying to find a linear combination of the columns to equate the vector of constants, which is in this case this. So I'll rewrite that later, but this is an observation that's interesting to make here. So going back to our initial problem, okay, I don't need the coefficient matrix really, I just need the augmented matrix, and I'm going to solve the system using Gauss elimination. So I will let you do that, okay? Do perform Gauss elimination on your own, maybe pause the video and try to do this, and try to recover the values of C1, C2, and C3. So doing Gauss elimination, this is what I got. So notice that for each column we can associate one of the variables. So now if I think of each row in terms of an equation, I can solve this system now using backward substitution. The last equation, the third one, or the third row, reads C3 equals 5. The second row, which is the second equation, now reads C2 equals minus a half C3. So that's minus a half times 5. So that's minus 1. And C1 is minus 1 minus 3 C2, which is going to be minus 1 plus 3, which is 2. So C1, C2, C3 is 2 minus 1, 5. And that's our solution. So those are the scalars that we need to obtain a linear combination of to find a linear combination of V1, V2, V3 that is equal to B. So similarly, if I have, just to give you an example, note, so when solving, let's say the system, I'm just making it up, 2x plus y equals 3, and minus x plus y equals 4, okay? The augmented matrix is going to be what? 2 minus 1, 1, 1, 3, 4. Okay? And one way to think about that system is we're trying to, right? If I look at that system I'm solving, really, if I can write it in vector form, you see, I can write 3, 4 here on this side. Here, this is y times 1, 1. This is x times 2 minus 1. So really what I'm trying to do from a geometric point of view is I'm trying to find a linear combination of this vector and that vector to give me the vector of constants 3, 4. Okay? So when solving a linear system, and that's true for any linear system. This is not true only for that example. It's a linear system with n variables, x1, x2, xn. We are trying to find a linear combination of the columns of the coefficient matrix So what are the columns here? They're here, right? V1, V2. So here we're trying to find a linear combination, okay, of the columns of the coefficient matrix. Say I call them V1, V2, Vn. I'll put the vector here on top of them just to emphasize that those are vectors, such that x1 v1 plus x2 v2 plus xn vn is equal to b, where b is the vector of constants. So all linear systems are essentially linear combination problems. Now look at number 20 in that same section, 3.1, number 20. In number 20, we're asked to show, actually not 20, but 21. We're asked to show that there are no scalars C1, C2, C3 such that where C1 times minus 296 plus C2 times minus 321 plus C3 times 175 equals 054. We're asked to show that this is not possible. How do we show this? Well, it's a linear combination problem that we can convert into, okay, a linear system problem, and then all we need to do is stack the vectors v1, v2, v3. Those are going to be the coefficient. The vectors are in my coefficient matrix for my linear system, and the vector of constants is going to be this, right? So this is just converting my linear combination problem into a system of linear equations. Just if you don't see it, look at the first equation. It just reads minus 2c1 minus 3c2 plus c3 equals 0. So that's basically equating the x coordinates, just like before. So what's our tool for solving that system? We do Gauss Elimination. Okay, I'll let you do that. Pause the video and come back. So what I got is this. Numbers are kind of ugly, but we'll see that something interesting happens. Okay, look at the last equation. Okay, how does it read? It reads 0c1 plus 0c2 plus 0c3. So essentially 0 is minus 678 over 23. The number is not important. The important thing is this is a non-zero here. So I can't have 0 equal to a non-zero. This is impossible, right? So I cannot have a solution for that system. So there are no solutions here. So this is how, with Gauss elimination, you can identify a system with no solutions. You'll have a whole bunch of zeros followed by a non-zero. The system has no solution. So therefore, the scalars C1, C2, and C3 do not exist. So this is like a good way of solving those two problems efficiently. So probably when you did it in 3.1, you converted your vector equation into a system of linear equation that you solve using whatever you could, like substitution, subtracting equations using techniques from sec 4, but now you've got Gauss elimination. That's a very efficient way for analyzing all of these problems. So every time you have a linear system, okay, put it in row echelon form using Gauss elimination and then analyze your linear system afterwards.